Okay, so this is lecture 4. Got a pen. And so we mainly covered the stress and strain. I wanted to get on to a little bit more on the method of joints during the lecture. Fortunately, ran out of time and didn't cover an introduction of method sections. So we'll do that now in this session, in this screencast. So you can start off with many types of stress. Can you think of different types of stress? Well, there's normal stress. So normal stress is when I'm trying to pull something apart. Ooh, and I've just pulled this apart. So pull something apart like that, and I'm strong. And then there is so that's direct stress. Then there's shear stress, where we've got the shearing action going on. And then what other kind of stresses can you think of? Well, they're obviously the two most common ones. The other important one that we'll be covering in this module is called bending stress. Bending stress is something specific for when we're putting a load onto our beam, and then we're going to get some bending going on there. So you can see, maybe if you've got a beam, you could imagine that we're going to get this bottom bit will be stressed in tensile, and the top bit will be compressed together, so that causes a bending stress. That's a new kind of stress, probably for most of us. And then other classic forms of stress, of course, is exam stress, work stress. But today I just really want to be talking about the normal stress. Okay, I think in future we'll introduce this topic very much at the beginning of the module, but it happens to appear round about now in the scheme of things. So it's quite simple. We if we have some force and we're applying it to some material here, so here we've got three elastic sort of ties there that are being pulled apart, and the more force this gentleman is applying, then the more elongation they're going to get. So more force leads to more stress. In this particular case, it's tensile stress, you're pulling apart stress, which will lead therefore to more elongation. Now these companies that sell these chest expanders, obviously these different colors are referring to how easy it is to pull these materials apart. And what they have is they have something called, associated with it, the Young's modulus or elastic limit. So basically you've probably come across Hooke's law, where you've seen that force is proportionate to a stiffness parameter times by the amount that we're going to pull the spring apart. And the Young's modulus is the equivalent of the stiffness parameter. But we don't like to use, when we're looking at structures, we tend not to are interested in the force in terms of what's going on inside the structure, but we're interested in the stress that's inside the structure. And the Young's limit, which will be a big E, and again, bizarrely, we're not particularly interested in how much displacement, although obviously these sort of things we'd be working out how much displacement the structure is going to move, but it's more interested in a non-dimensionalized form of elongation, which is called strain. So this E value here now becomes independent upon how many previously the K value would be dependent on how many things I'm using, what sort of force, or how far they're extended. But now if we're using E, what's good about this is that the E value for the black is going to be the same, whether I'm trying to pull it apart one black tie, or whether I'm trying to pull back 5 of them. So force per unit area is our stress value. The intensity of the force acting normal to the area. So normal stress, that's how it gets its name. So we've got a normal area, and we're pulling it apart, and it's perpendicular to that. So that's why it's called normal stress. And the reason is, I've kind of tried to explain, is in terms of whether this material is going to fracture or how much it's going to elongate. So let's say I've got a big bar there and a little bar here. So I'm pulling this with a certain force, and I'm pulling this with a certain force. Now this, and if it's the same material, this one will start moving a lot more. Okay. However, the forces are the same, so that doesn't seem to make sense. But if I look at the stress, which is the force divided by the area, I can see that I get a much lower stress inside this bar than the stress inside this area. So area 2 here is a lot smaller than area 1. Okay, so area 1's got a bigger value, so the amount of stress inside is lower. And that's why we're interested in looking at the stress value, because that will then give us an idea of working out how the load of the structure is going to be affected by the forces. For direct stress, we normally use the symbol sigma, and this would be an imaginary case where what I'm got is this thick bar, and then I do an imaginary cut in my thick bar, and I set that area to be perpendicular to the force that's pulling it apart, and then I imagine I can see inside the bar here. And what can I see inside the bar? Well, I can see lots of little stress trying to when I do a cutaway inside. So this is the argument is that if I do a little cut through the beam, what's that stress inside going to be? Well, that stress inside should be, if I take that stress and multiply it by its area, let's do a multiplication symbol, that should equal the force that's being pulled in that direction. Notice how the stress inside the bar, however, is now going off in this direction, while the external force is going off in this direction. So internal forces are pointing inwards to the bar, and that's representing something, a bar being pulled apart, whereas if I was compressing it, I would be pushing into the bar, and then we would end up with a stress that's going in the opposite direction. So stress is going to be applied load divided by the cross-sectional area, and we can see why we want to use it. So the units, we're going to use newtons per meter squared, we're going to use pascals. Normally that would be used for pressure, but it dates back really far in history when they started using pascals for stress calculations. So c'est la vie. And then we've got, because 1 Pascal is such a small amount of force, we tend to use lots of pascals. So we tend to use megas and giga values. So mega in particular for most structures, most materials can go up to 5 to 200 or even not more megapascals. So since we're dealing in millions, I tend not to like using this. Maybe I prefer using mega newtons per meter squared or simply 1 megapascal. The other option for structural engineers who don't mind using newtons, but don't want to be using these values of indices, megas or 10 to the 6s. So they get rid of it by looking at how many newtons there is per millimeter squared as opposed to per meter squared. So here we have a direct stress on a 20 diameter cylinder bar. It's loaded in tension, means we're pulling it apart by 10,000 newtons. So the force that we're pulling apart is 10,000 newtons. The area, well, the formula I use for area is pi d squared divided by 4. I'll convert my millimeters, 20 divided by 1,000. I'll convert that into meters, so that makes it 0.02. So, and then I'll put that in there, so I've got everything in my lovely SI units. And then I work out the answer, and I get a very big answer. Press my eng button on my calculator, and then I can rewrite this in terms of mega. So there we go. So here we've got two springs, one which is quite stiff there, so high value of E, and here we've got another one where applying the same sort of weight to there, and we've got a lot of extension. Okay, now if I put one weight on my spring, I expect it to extend a certain amount. If I put two weights, then I expect it to extend two of those amounts, and I keep going up. So put 3 of them on, same amount, sort of thing, 4, and so on, 4. Okay. Okay, so not surprised there. So in order to just look at the property of this spring, or the property of the structure that I'm pulling apart, we want to get rid of elongation, and as I've already described, this is where strain comes in. So even things like metal behave a bit like rubber, although in this particular case you get this process called necking, and so the material is necking, also known as wasting, where over a certain, which would be I suppose about here, so over a certain section that starts to form in dramatically, but this bar and this bar is the same, so even if you look at these sections here, you can see that that seems to be longer than that quite clearly. So strain is useful because it kind of non-dimensionalizes how much extension we're going to get for a certain stress, and it's simply found by the extension divided by the original length. So you can see why we're doing that. Once we introduce strain, we might as well introduce another term, although we won't be using it for a while, and that's Poisson's ratio. So if that effect is when I start pulling something apart, it then starts well, kind of wasting, isn't it? So it goes in, gets narrower as I pull it apart, and this will happen if I was looking at a 2D shape there. I was pulling it apart like this. It would go in this side and this side, and kind of in equal measure. And if we were not losing volume, the percentage that we go in from the top is 50%. The percentage we go in from the side is 50%. So our total volume would be the same, and that would be an example of a Poisson's ratio of 0.5. Poisson's ratio is defined with normally this new symbol. Anyway, I'm getting off track slightly. Should be talking about the strain value. So the strain, we use epsilon, and it's simply defined as the amount that this elongates divided by the original length, straightforward. Here's an example. So we've got our 1.2 meter long bar. So the only thing that's difficult with this problem is to decide which units to work in. Probably most sensible to work in whole numbers. So I'm going to get rid of the 1.2 meters and replace it with 1,200 millimeters. So it's extended by 1 millimeter. So 1 millimeter divided by 1/1200 millimeters leads me to this number on my calculator, and this value keeps popping up a lot for strain, because strain tends to give you values of 1 times 10 to the minus 3, minus 10 to the minus 4, 1 times 10 to the minus 5, those kind of numbers. And so that is often replaced with a symbol that looks something like this, either mu epsilon to represent microstrain. Sometimes people are lazy and they just write mu. Okay, so 1 microstrain equals this symbol, which equals 1 times 10 to the minus 6. So what we've seen? We've seen that force gives me more stress gives me more elongation gives me more strain. There's only there are three really important equations we need to learn, and that's going to be Young's modulus, or modulus of elasticity. That's the E value. Is going to be stress divided by strain. So that's first equation, and of course that might not be valid. We might be looking at something that's gone past the elastic limit, the yield stress value, and that might not be a valid equation to use. Stress is going to be defined as force divided by area. If you're talking about most forms of stress, you can use the symbol sigma. Strain is going to be defined as elongation divided by original length, and for most scenarios we're going to use strain as an epsilon. Here's some values of Young's modulus, so don't forget this is referring to a stress-strain plot. We've got stress, got strain, and then we've got basically the gradient here. So here we've got rubber down at 3.3, so that's my rubber, very low flat. Young's modulus value and gradient, and then we've got steel, which is going to be going shooting off in a very high extent like that. Okay, so what do we want to do to work out this problem? This is very much in the form of an exam type question. So we've got 2 meters, we've got a known force, we've got a known area, we've got Young's modulus, calculate the extension. So go to your equations and grab the closest equation that looks valuable. So that's going to be the change in length equals the original length times the strain. Okay, I've got the original length, I don't have the strain, so how am I going to find the strain? Well, I'm probably going to have to go to this equation to find the strain. So strain is going to be given as the stress divided by the Young's modulus. Yes, so swap those two terms around, and that's going to be what we're looking for. We don't know the stress though, and stress is going to be given as force divided by area divided by Young's modulus. So that gives me the force, 25,000. Let's put everything in SI units. I'll drop the A down here. So we got A is 40 times 10 to the minus 3. Square it. And we've got E, which is going to be 120 times 10 to the 9. Okay. So let's whack that in my calculator. Let me know if I've gone wrong. So 25,000 divided by 40 times 10 to the minus 3. Let's square it, and then times by, I'm doing brackets, 180 to the 9, close brackets. Right, so that will therefore give me my strain value. It's quite small, so that is 86 microstrains. Actually 87. And then I want to come back and work out the actual extension, so that's going to be change in length, 87 times 10 to the minus 6 times by the length of the bar, 2 meters. Right, so that is going to be 1.74 times 10 to the minus 4 meters. It's not really worth dealing with. Okay, I'm going to do a method of joints example using this framework. If you can't set up this framework, then we'll quickly do that. So I'm going to use equilateral triangles, 2 meters long bars. I'm going to have a load hanging off my D point here. How do I work out the reactions? So we got equilateral triangles. Good to draw a little bit of geometry next to you. We've got 12 newtons hanging off here. Let's label it up as A, B, C, D, E. So, I've got a reaction at RC, and I've got a reaction RAX and RAY. I will take moments about A. The distance from here to here, so if that's 2 meters, that's going to be 1 meter, so that's going to be 12 times 1. And the only other one I've got is this reaction force here, so that's 4, so minus 4 RCY. Therefore, RCY equals 3 meters. Oh, sorry, not 3 meters. 3 newtons. I need a break. Right, so got that. 12 newtons coming down. I can do this in my head. Sum up the forces in the y direction. That's going to give me RAY plus RCY. Take away 12 equals 0. Therefore, RAY equals 9 newtons. Okay, so that's straightforward. So got 9 newtons going that way, 3 newtons going that way, and you can see that RAX is going to be 0. So let's now come on and saying that we wanted to work out the AD value, so the internal force in AD. So we'll come back to this problem. A, B, C, D, E. And I've been told that I want to find the internal force in that bar. What am I going to do? Well, for method of joints, you have to first of all write all your forces on your diagram. So we've got 9, 3, 12 coming down. Put a little bit of geometry on things. What else? I think that's about it, isn't it, really? So I have been asked to find AD, and now now comes the magic. So the method of joints is that you imagine that you can cut around the joint, and then you're going to expose the internal forces AD and AB. So you can rewrite this as a diagram that looks like this. So you've got AD going off in this direction, and then you got BD, whoops, BD, oh no, I haven't. I've got AB going off in that direction. I definitely need a nap or a break. Okay, so that's 60 degrees. I've got 9 being applied there. So any external forces, I need to write them up. And I've cut through those 2 beams, which then exposes them and becomes those forces AB and AD. This is an example where I could box clever and cut myself out a little bit of work. So got 30 degrees to resolve vertically. If the question's only asking me for AD, I'm not interested in AB, what can I do? Well, AD is pointing vaguely upwards and vaguely left to right. AB is pointing just left to right. If I resolve upwards, I can then use this free body diagram and isolate my AD value. So AD is going to swing through 30 degrees, so to make it to point upwards, it's going to have to go through a cos. So AD times cos 30. And then we've also got plus 9 kilonewtons going upwards. So then that leaves us with AD equals minus 9 divided by cos 30. And then you could go to your calculator, stick that in your calculator, see what it gives you before you press the SD button, and it'll give you a value of minus 6 root 3. And if you're going to present your final answer, then at that stage you want to press your SD button. So what would that give me? So give it a go. Don't try and sort of like work out the irrational numbers, just use your calculator to do the work. So minus 9 divided by cos 30. Yeah, so so that's telling me it's minus 6 root 3. Press the SD button, and then I've now got minus 10.392. I think I'm working in kilonewtons. And because it's a minus, if you have minus answers in internal forces, then they're in compression. If you have positive answers, then they're in tension. So that's found that value using method of joints. Okay, let's say we wanted to know what stress is going on inside this beam and what stress is going on inside this beam here. What would I do then? Well, so I've done method of joints around A. I've skipped this beam here, I'm not interested. And now what I need to do would be to do a method of joints around the D joint. So let's do that. So we're going to imagine now, let's go back to my red pen. I'm going to imagine now that I've done that one. But the question or whatever is asking me to find, is asking me to find what is the stress inside this beam, this member. So it's A, B, C, D, E. That's 12 coming down, that's 9 coming up, and that's 3 coming up. So we're going to do a method joint around the D joint, so we're going to do a method joint around there. So then next thing I want to do is to draw a little free body diagram showing those forces off. So we've got now AD, and notice that AD was pointing upwards, okay, but when I cut it around this joint it now points downwards, and the reason for that is because the internal forces are always acting opposite one another. So if I cut around one joint it's going to be pointing that way, cut around the other joint it'll be pointing in the opposite direction. So AD is now that value, and the fact that I got AD equals a minus value, I put it in as a minus value in that sense. So it's actually kind of pointing in the opposite direction, but we're using the minus from its value to tell us to make it point in the right direction. So this one, we then have a force coming straight down of 12, I think it's kilonewtons, could be newtons, kilonewtons coming down like that, and then we've got this dB, which we've been asked to find, and then we've got this dE. So we know what that value is, we've previously worked it out. We notice that dB is vaguely pointing downwards, so again we can box clever and just do one calculation to find out what dB is. So I'm going to sum up my forces in the y direction. I'm going to go downwards, and so that then gives me that AD needs to swing through 30 degrees to go downwards, 12 is going downwards, plus dB needs to swing through cos 30 to go downwards. Okay, what was I going to say? I was going to say, yeah, so notice I've done something that you might not have come across before, or certainly not in the notes, that I've decided to make downwards to be positive for when I'm doing my summing up my forces. Well, this is fine, but the reason for that is because everything's vaguely pointing downwards, so it's much easier to think of things, the 12 pointing straight downwards, so it's a positive, this having to swing through 30 degrees, point straight downwards, so that's that makes it that little bit easier. So what we want to do is rearrange this to find the dB value. So dB is cos 30 equals minus 12 minus AD cos 30. Notice these minuses follow you around, you have to keep a track of them. Now we're going to substitute in our value for minus AD. The preference there would be to use the irrational number, or you could even go back to the cos value. So what do we have for the cos value maybe? So here we had AD was minus 9 divided by cos 30. Okay, so we could, if we wanted to, put that in there, I think. Okay, so we've got 9 divided by cos 30, and the reason why I put the cos 30 one in there is because then I don't have to bother looking up this cos 30. I can see cos 30, take away cos 30, and what I've forgotten is I've forgotten the minus sign there. Right, so I've got a minus 12 plus a 9, that gives me a minus 3. So my dB value is going to be minus 3 divided by cos 30. So now is a good point maybe to grab your calculator and stick those numbers in. So minus 3 divided by cos 30, and let your calculator do the work out the irrational numbers, and the calculator is telling me minus 2 root 3. Okay, which you can then press your SD button and find that out. Real money equals minus 3.464, I think I am kilonewtons, and that's going to be in compression. So if I'm pulling down here, then it means that this bar and this bar are both going to be compressed. You can think about the framework and how it's happening and whether that makes sense. So I found that AD was minus 6 root 3, so to 2 decimal places that's minus 10.39 newtons, and dB, so that's my AD1 was that value, and that my dB, so that's this member here, was minus 2 root 3, which in real money is minus 0.46. What I can do next is use MD solids, nice cool code like that, and then put the basic structure in and then compare it to the computer solution. So the computer solution doesn't use minuses, but it does tell us that it's in compression. So we can see that we've got that value is correct, that value is correct. I should have stated that they are in compression. Okay, are we happy? Right, so the next approach is not using method of joints, but using method of sections. So imagine we had a problem like this, and the exam question was, can you tell me what the stress is in this DE beam? Okay, well, given that problem, and that we had this weight there, so that's all nice and straightforward. I can work out the reactions just by inspection and so on. So I've got 6 kilonewtons, 6 newtons there, say, and 6 newtons there, and 12 newtons coming down in the middle, and I want to know what the stress is inside that beam there. So if I can do method of joints, I would have to start with a joint where I'm only going to cut through 2 members. So I've only got 2 choices. I could cut through here, or I could cut through this point here. Let's say I decided to cut through the joint on the left. I would then have to start moving through using method of joints, jumping from one joint to another joint, always going to a joint where there's only going to be 2 unknowns. So notice by the time I've got here, I know what that value is and I know what that value is, but this is unknown, so I need to go up. Okay, now I know what that is, I know what that is, I know what that is. Can I go to this one here? No, because that would be 3 unknowns. I have to go to this one here. Okay, now I know what that one is, so this is unknown, so now I can go up. Okay, and we're looking for finding the DE term. We know this one, we know this one, we don't know this one, we don't know this one, so we can now jump down to the D joint, take a cut through it, and we can then apply our magic resolve to left to right horizontally, and we'd find DE. That's a lot of work. That's going to make us very angry. So is there a way of doing method of joints where I just cut through all around the section there, so we're just cutting through like this? Yeah, well, of course, let's call it large method of joints. Yeah, let's just do a method of joints all around there, and which ends up cutting through the DE. But the slight problem is now we've cut through 1 member, 2 members, and 3 members. Is that allowed? Because method of joints only lets us cut through two members of that are unknown at each time. This time I'm cutting through three members that are unknown. Can I cut through three members? Well, yes I can, because I'm going to do the same sort of principle here. So I'm going to keep my framework on the left. I have to keep my external forces. So they are my external forces. That's my load and that's my reaction. I'm cutting through those members, and then by cutting through them I'm exposing their forces inside, and I'm going to label them up in terms of the joints that they're called. Okay, so this example is on Blackboard, so you can find it in the week video. I think week 4 or no, week 5, sorry, no, week 4 video, so I won't go through that one now. You can look that video up. But why is it I can solve this whereas I couldn't solve the method of joint? Well, I'm going to stick on another equation. With method of joints, we are resolving in the y direction. Well, actually we should probably start off with the x. We are resolving the x direction and the y direction, although in my previous examples all I needed to do was resolve in the y direction. So we're using these two equations. Sometimes we're just using one of these equations to find what we want. Here we have three unknowns, so I need to stick on a third equation, and my third equation is going to be take moments. Where I take moments is perfectly up to you. Choose any joint you like. Any joint you like. Usually it's good to go for joints where there's two unknowns, so that would be a good classic point to take method of joint. To take moments about there. So I might want to apply my method of moments, summing up moments at that particular joint there, which I'm guessing is K joint. Okay, but you could take it other points. You could take it there. I've seen people take it there. It's just as well. The disadvantage if you take it, say maybe at joint A or this joint here, is that so that's A, B, C, D, so that would be at the joint D, is that those joints, if you don't get rid of the two unknowns, tend to leave you with a set of simultaneous equations which you then have to solve. So it's a little bit more maths involved, so it's probably best not done. Best to go for something which kind of looks like as if it was almost a hinge, okay, with two reaction points coming out from it. Thank you.